atom. And in the Bohr model of the hydrogen atom, you could imagine that you have a nucleus. And then you could imagine that there are different energy levels that the electron could be at. So you could have it at its first level, or its second level, or its third level. And eventually, the electron would be so far away that it would no longer be in an orbit. Now, the Bohr model gives the energy of each level, E sub n, and it quantizes it. It says that there are specific energies. There is an energy with the first level, with the second level, with the third level, is equal to minus r, now I'm going to write here infinity, and I'll describe this in a second, times 1 over n squared. So this is an inverse square law, and R infinity is an energy term which is the energy required to remove an electron from the lowest energy level out of orbit. So it's just completely no longer in orbit. It's knocked right out of orbit. Now we have a minus sign here from the first law of thermodynamics. If you have to add energy to remove something, then that's a positive, then it's being removed, and you've added energy to the system. Therefore, if the zero energy is when the electron is completely removed, the energy in the orbit must be negative compared to zero because you had to add energy to remove it. And when the electron is completely removed, that's when you have zero energy, okay? Now, what we can say here is a very simple proposition. The energy of the photon is equal to the energy of the electronic transition, okay? Now, here's where a challenge comes in. There are two types of processes. You had your absorption and your emission. When you had an absorption, energy was absorbed in the absorption spectrum, but when you have your emission, energy is released, okay? So when the energy is released, we have to put a negative sign in here. When it's absorbed, we have a positive sign because released is an exothermic process. So I can now say the energy of the photon is equal to h nu, Planck's constant, times the frequency. And I can say this is equal to the energy of the final state minus the energy of the initial state, okay? And recognize that this switches between emission and absorption. In absorption, you go from a low energy to a high energy, okay? So it would be the larger number minus the smaller. In emission, you've excited the electrons, and then it relaxes down to a lower energy, okay? Now we also know that C equals lambda nu, so we can now write this in terms of wavelength, and we can say that hc over lambda is equal to, now I can bring out the minus R infinity times now E sub nf minus E sub ni, excuse me, but this is 1 over n sub f squared minus 1 over n sub I squared, okay, which now we can say 1 over lambda is equal to, now if I bring this minus sign in here, okay, I have a 1 over n sub I squared minus 1 over n sub f squared, and now I have my minus R infinity over hc. And this is the Rydberg constant, okay? So the Rydberg constant, so this is the same as 1 over lambda is equal to, except we got rid of the minus sign because we switched these, is equal to R times 1 over n sub I squared minus 1 over n sub f squared. Now, there are two things to recognize. In the Rydberg equation, this was an N1 and an N2. Here, we have to be careful. We have an initial minus final, and if the process is absorption, we write it like this. But if the process was emission, we would say that the energy of the photon is minus the energy of the electron transition and the sign switch. bottom line is that it's always the larger, 1 over the smaller number divided by minus 1 over the larger number. Now, if we want to calculate the value of R infinity here, we can say that R is equal to R infinity over hc. So R infinity, which is an energy term, is equal to the Rydberg constant times Planck's constant times the speed of light, which is equal to 1.097 times 10 to the 7th reciprocal meters times 6.626 times 10 to the minus 34 joule seconds, and then times the speed of light, which is 3.00 times 10 to the 8th meters per second. Okay, and now we come up with 2.18 times 10 to the minus 18 joules. So what's important to recognize here is that the Rydberg equation was derived from empirical data, but we can understand it conceptually from the Bohr model, where we're saying that electrons undergo transitions. So if an electron goes from the n equals 2 state to the n equals 1 state, energy is lost and a photon of light is kicked off. On the other hand, if energy in an absorbance spectra goes from the 1 state to the 2 state, this means a photon of energy was added to the system. And because of that, we have a sign change depending on whether we added the photon or we removed the photon.